Good morning. On behalf of the co-organizer, Victor Solo, and myself, DuBois Bowman, I'd like to welcome you to this morning's session, Skeptical Connectivity, Time for Something Completely Different. So just to give you a little bit of background, there are a group of us who periodically give symposia or even educational courses, and we refer to ourselves as skeptical neuroimagers. So you may have seen the title appear in some of the previous programs, and so I'd like to therefore give recognition to Martin Lindquist, Tom Nichols, Victor Solo, Mark Woolrich, and there have been several others who've pitched in throughout the years. So this year's topic on connectivity, one can hardly miss sort of the emergence and popularity of connectivity work. Just a quick Google search yields, on Google Scholar, yields 969,000 hits on the topic. There are major initiatives around the world, the one in the U.S. known as the Human Connectome Project, that also reveal the significance of the topics. And then year after year at this meeting, you really see the high prevalence of connectivity topics throughout the posters as well as the oral sessions. And I think we've had a lot of successes. So we've observed consistent patterns of resting state connectivity. Scientific inquiry into connectivity has drawn links between learning and memory tasks, neural development, psychiatric disorders, and neurological diseases, just to name a few. Yet, in the spirit of the group as skeptical neuroimagers, we'd like to bring a message of pause and reflection, and that's just to suggest that potential pitfalls still remain. And we don't intend to bring a message that's entirely negative. It's just to draw pause again and to realize the assumptions that are made behind models, and then to make interpretations in context of those assumptions. So just to list a few topics that I think are in line with those comments. Inferring cause is really tricky, whether from connectivity or other types of brain imaging data. Time-varying connectivity, the plot shown here shows time-varying connectivity produced from sliding windows of varying lengths. And as is well known to many of you, often what you find is a mere reflection of the window size that you select. Reproducibility on connectivity is a very important topic given the high dimensionality. And then another point is wasting less data. Because of the large high dimensional aspect of the problem, we almost immediately reduce to ROIs and draw connectivity between the ROIs, which is necessary on the one hand to reduce the billions of voxel pairs that we may have, but we should also keep in mind that we're discarding data, and the data that we use may not be entirely sufficient for the original data. A few other topics, multimodal connectivity. I've done some work in that area as well, so estimating functional connectivity, informed by structural connectivity, network comparison methods. And it's not. I know that there are a lot of contributions from you and others here at this meeting in these areas, and so it's not to say that those aren't useful contributions. But for all of these things, I think it requires sustained attention by the scientific community. Direct versus indirect correlations, and there's a image here again, a topic that's well known to many of you, but partial correlations or indirect correlations are typically more sparse, and it makes us wonder about the potential pitfalls of not using partial correlations along the lines of perhaps spurious results. Reproducibility is so important, I've put it here twice. So today's lineup of speakers won't necessarily tackle all of those things. I just wanted to prime the presentations by mentioning those topics, and today's speakers will elaborate on some of those things and then present some fresh new methods that they've developed recently. So the first speaker is Dr. Thomas Nichols from Warwick University.
morning. Thanks for getting up and joining us to think critically about statistical methods. Before I start my talk, I'm just going to talk about, I couldn't resist putting in a plug for a poster that is very skeptically oriented, but not at all about connectivity. This is some work that my collaborators are presenting today, where we skeptically examined the ability of traditional software tools to control false positive rates using resting state data with task-based analysis methods. And we're disappointed by some of the false positive control. So I won't go into that story, but do check out that poster. It's quite fascinating. Okay, so what motivated me is as I looked at some of the methods used for in graph theory and how graphs were analyzed in brain imaging was there was a lot of terms of graph theory or network analysis, but not so much of the emphasis on modeling. I really look for what was the models that are being used when we talk about when they're talking about measures of graph complexity and the like. And so what I looked for was, are there ways that we can find actually statistical or stochastic models that actually could fit the data and then even predict what would a new graph look like from this data. So the motivation here is I'll first talk about a class of models called mixture models, Erdos-Renyi mixture models. How we evaluated those with real brain data and then extended those to multiple subjects. And then I'll do a quick mention to another work of extending these block models in the service of a traditional network measure. Okay, so we're talking about graph data. It consists of edges and nodes. And this is a very small network. I guess I can't really point to anything. So, and what we see here is that there maybe is some structure here. Maybe if you look carefully that there is some groups of nodes that seem to be more related than others. And so what we're looking for is something not only to see if we can find that structure, but can we find that structure respecting the fact that this is not just one graph. Actually, there's a whole stream of graphs that we'd like to observe. I would like to be able to, whatever I'm doing, I would like to reflect the uncertainty in the structure. I want to try to find what is the probabilistic model that describes not only this graph, but then a whole family of graphs that are similar. So I'm going to be trying to find a stochastic model for this data. So if I try to do that, one of the ways you can do that is with something called a stochastic block model. And what that does is it assumes that there's some homogeneity. I don't necessarily know what these groups are, but if I can find these latent groups or classes, within those classes, I have a homogeneity of connectivity within and between the different groups. And notice this doesn't necessarily mean that there's more connectivity within individual groups, but that there's just simply a homogeneity. So if we just define this a little more carefully, it was Dowden's paper that gave the name Erdos-Renyi mixture model. Erdos-Renyi is the name for a very simple stochastic model for graphs, and not a very useful one. And that is that the connection probabilities the connections occur with a homogeneous and independent probability. That's not very good for biological networks, for the whole network. But if you can block up the network, then it's actually not such a crazy, and we do this all the time. For example, Gaussian mixture models are one way to use a very simple model, a Gaussian model, to represent more complex structures. And so we're doing the same thing. We're using a simple graph model here, the Erdos-Renyi, to assemble into something that's more complicated. So the key thing that I was drawn to with this work from Ruban's group is that they had a practical implementation. Stochastic block models have been discussed in the statistical literature for some time. People write long papers about the probabilistic properties of stochastic block models, but then when you get to the end of them, they'd say, oh, of course, we have no way of inferring what these blocks should be, how many blocks should there be, which nodes belong to which blocks. That's left for future work. So it was this work to me was one of the most practical methods that I saw, because not only did they describe it, they produced R packages that worked really, really well. Mixer was the original one, and they've recently updated that. I think a student of theirs have created another one called Block Model. So we wanted to put this to work, and so I had a joint student with Ed Bullmore, and we have this problem is that we'd like to know how well this method's working, but of course on brain data, resting brain data especially, we don't know the true answer. We don't know the right answer. So Ed had been working with the model organism, the C. elegans, and this actually is, so first of all, this model, this data originates as binary. So we eliminate all issues of how to threshold and make binary data out of continuous measurements. And we also have a rich amount of information on the anatomy of the worm. We have different types of, the neurons are organized into ganglions. They have different types. There are different types of connections between the different neurons. We also know where they are, so we know their anatomical location. We also know something about when the model, when the organism is developing from a single cell and growing into an adult worm. We also know when these neurons get born, so to speak. So we also can look at that. And also we can look at the lineage distance. This has to do with the sort of genetic origins of each of these neurons. So what we want to do is to take this Erdős-Renyi model and compare it to some other methods for blocking up data and compare it with these other measures. Now, for the measures that are categorical, we now have the estimated classes in this true category, so we measure that with the adjusted Rand index. And then for the things that are continuous measurements on each of the neurons, we use the interclass correlation to see how well our estimated classes capture the variance in these continuous measurements. So here is the Erdős-Renyi mixture model on the top. So we're seeing the reorganized adjacency matrix of all these the neurons in the worm, and on the bottom, two methods for modularity, which are kind of the sort of dominant methods used for sort of clustering graphs. And what you see is that the Erdős-Renyi is able to identify these hubs. So groups 5 and 6 actually have connections across the entire set of nodes. And then you also have some areas where there simply are what I call non-modular connections. So group 1 and 2 are sort of interconnected, but they're distinguished by the fact that group 2 has connections with group 8 there. And in contrast, the modularity can only do one thing, and that is try to find groups that are most as interconnected as possible with themselves and as little connected with other groups. And you can see it doesn't seem to represent the structure very well here, and you can see there's a lot of off-diagonal structure. And this seems to be, I think the Erdős-Renyi captures more structure, interesting structure, and we then try to measure that quantitatively. In terms of on the left is the adjusted Rand index, so how well do our estimated groups line up with the categorical labels of the neurons, and you can see that we're doing just about as well as the other two methods, but in the interclass correlation, the measures where we see how well the estimated blocks can explain the quantitative measures, that you can see that this mixture model seems to do a better job in most settings than the two other modularity-based methods. So this is suggesting, so we use this to, I'm not particularly interested in worms myself, but this was a case where we actually had a biological network of a nervous system, and it seems that this model is more flexible, and hence gives us some confidence that when we go to apply it to humans, that we're going to get some meaningful answers. But we had a problem. The Erdős-Renyi mixture model is only for single networks. And of course, we're interested in generalizing to populations of subjects. And if we had gone and fit the Erdős-Renyi mixture model each to a set of subjects, we would get results like this. The number of classes and even the identity of what those classes would not be constrained across the subjects. And so it wouldn't be obvious how we could then use this to make inference if these groups don't even mean the same thing across subjects. So, and also the other thing is that, of course, whenever we do inference on a group of subjects, we usually want to have covariates. We want to either adjust for some things like age or gender. Maybe we're interested in the effects of smoking or what have you. So we want to extend this, and this is work with my then student, Dragana Pavlovic, who is now with Thomas Yeo. So if I write down the Erdős-Renyi model, this is what it is. It basically says that our edges arise as a Bernoulli. That's just a coin flip distribution. And now we propose three different ways to extend this to multiple subjects. Crucially, for all three of these approaches, we assume that the block structure is the same for all subjects. So that means these blocks will mean the same thing. And then we can take the simplest model where we have no covariates, and then, of course, if we have n subjects, that means we'll have n coin flips at each edge, and the appropriate model for that is a binomial distribution. And then the more interesting cases then are when we have covariates, and that's the second case. If we want to assume that our covariates homogeneously affect the whole network in the same way, then that is, well, it's basically like a logistic regression, but those coefficients are common across the whole network. And then the next most general case is what we call a heterogeneous Bernoulli mixture model, and that's basically like doing a logistic regression, but separately for each block. So this is the most flexible one. This lets us use different. We have a set of covariates, and those covariates will be estimated uniquely at each different block and block combination. So this I think is a really sort of nice way, because I think we're all really comfortable with regression, and this now lets us go and analyze this binary network data in sort of in our comfort zone, at least I think. So let's illustrate this last model on some data. This is, sorry, just some cartoons of what these three different models do. This is the binomial mixture model. It's assuming everyone is homogeneous. The homogeneous Bernoulli mixture model is allowing for changes. So, for example, if connectivity tended to decrease as you got older, then the homogeneous mixture model then could account for that like this. And you can see with the covariate describing a homogeneous effect over the entire network. And then the most flexible one is where we actually say, you know what, each one of these different blocks within and the between block connectivity needs to have its own regression coefficients, because we're going to see different relationships over the different blocks. And that is indeed the model that we'll look at a little bit more, because I think this is probably the one that's most flexible and most people would be interested in. So we use data from Ed Bulmer's lab. This is data from controls in patients with schizophrenia, the 25 subjects, resting state data collected as part of a drug study, but we were just using the placebo drug here. They use wavelets to find the correlation, and while focusing in on the frequencies that they're interested in. We use, after a Fisher transform of the correlations, we used FDR at 5% to binarize this network. Of course, that's a whole other can of worms, which I will not get into, is how all the choices you have when doing that. And we want to look at the following covariates. We had patient control status, we have age, we have a IQ, which is supposed to represent the prodromal the IQ in the patients well, and then we also have measures of motion. So the first thing to show is that when we estimate this heterogeneous mixture model, we found 24 regions, and importantly, those regions made sense anatomically. So here I'm illustrating them grouped into groups of 6, but with the colors labeling each of the individual distinct 24 groups. And so we able to sort of say that okay, this is the first sort of test of plausibility. Are we getting reasonable blocks out? And we seem to be. These seem to, and we've organized them here into sort of reasonable groupings here. And then we have this is the estimated reorganized adjacency matrices. And now actually I haven't used the fitted means here. I'm just showing you the most basic representation of the data after it's been reorganized according to these estimated latent groups. So we can sort of do a little sort of inspection by eye here, and you can sort of visually see that there just seems to be relatively less connectivity overall in the patients relative to the controls. But now with this model, we can actually go and inspect these things more closely, edge by edge, or sort of block by block, I should say. So first of all, if you just look at this, and I really wish I had a laser pointer so I could point these out more, just showing these are this is if you look at the node 4, if you look across the row, you see node 4 is closely connected with itself, but also connected to other regions 20, 21, 22, and this seems to be a sort of a parietal set of nodes that sort of are linked together. Here we see visual nodes. Again, if you look down the line of row 3, you can see that they're connected to these other regions 7, 13, and 18, again, which are visual networks, which makes sense. And lastly, we have some cerebellar networks. So again, that these areas, the areas make sense, and the connectivity, the baseline connectivity that we find also makes sense. But now we have a statistical model. We can actually go, and so here we are. We have z-statistic images. So we've thresholded these with FDR, and all the things in color are showing the changes. So the first one on the left is showing what we kind of saw by eye in the other picture, which is there's just a gross difference between the patients and controls. The controls generally have more connectivity between each, but you can actually see which areas now are most greatly affected. The age effect is less consistent, but it also, I think, makes sense. It's a negative effect, and this is showing that the older the subjects they are, the less connectivity they have. And of course, there's lots of reasons why this might be. This could have something to do with data quality, but we have been controlling for head motion, so hopefully this is a sort of a more unique age effect. So that was the irrational mixture model I wanted to talk about, and don't have time, but I just wanted to give you a quick preview of some other work that we're working on with my other student, Suresh Afsani, And he has been taking this stochastic block model and using it to sort of bring new light to the rich club network measure. So this is a measure that talks about basically how wired are the most sort of connected regions, and are they mostly connected with themselves. So this is something that you do by sorting your edges by their degree. Now we have a fitted stochastic model, so we actually can rank our blocks by their average degree, and then we can create a similar measure, which Suresh has called a rich block. And what's really neat about this is that one of the slow things about rich club is that you have to do a resampling exercise to come up with a null distribution to then see how significant these rich club coefficients are. But because we have a stochastic block model that says that we know how to generate new realizations of networks, we can do this very quickly because we can work out what the null model is under the sort of the rich club null and generate realizations from this very quickly, and it allows us to do things that, for example, we're able to compute rich block coefficients, inferences on dense connectomes. So this is from the Human Connectome Project, 30,000 by 30,000 dense connectome data, and we're able to identify the rich coefficients, again, because of the computational practicality of this. So that's poster 3973, presented on Thursday, and I invite you to visit that as well. What I focused on today was talking about a approach of using a stochastic block model, and basically encouraging you to think about sort of ways of using sort of statistical models well, everywhere. So basically what motivated this work was simply that the graph models, the graph analyses that I've seen didn't reference an explicit parameterized model, and I thought there would be opportunities from that. And I think we're right that when you actually pose and then estimate a model that is a generative model for your data, you can start doing sort of more and richer inferences. And in particular, the Schrinning mixture model seems to capture biological structure better than just simple modularity. And we're using this to try to sort of give new insight into the existing graph measures. So I'll stop there. Thanks, everyone. Do we have questions, or we just move on?
Sure, we'll take a minute for questions.
I guess we have 1 minute for questions. Is there any? Yes, over here.
So cool talk. So I definitely appreciate the utility of generative models. I'm just curious with your parameterization whether or not you can see an extension to a case where the block membership is changing parametrically, particularly with development, so that you're parametrically modulating not the probabilities within a block, but the way that subunits can shift their membership.
So basically changing, yeah. So I haven't been working, so there's another class of models where they call mixed memberships, so you can have overlapping memberships, but I had not thought of dynamic memberships. I think you definitely could motivate that, but it'd be challenging, I think, to describe how things change over time. But it's a good direction. Yeah.
So the block models that you're using implicitly, they make the assumption that the edges are placed independently, but that's certainly not the case with correlation matrices or...
That's right.
Is there any plans to extend this so that the edges are no longer independent, or something more compatible with?
That's a fair... So you're alluding to the fact that when you take a correlation matrix, especially if you take a correlation matrix with not very much data, you can get what I call Wishart noise, so basically streaky appearances, and some people have found that this actually can even give you small worldness. So we haven't thought about that. I mean, I think if you block up if there is strong dependence, it's going to be sort of blocked up into smaller groups, and that will degrade the performance of the model. So, but I haven't thought about how to do that.
Thank you.
Good question, though.
Okay, thanks, Tom. The next speaker will be Chung from the University of Wisconsin.
This talk is about constructing large network. When I say large, I mean really large. So this is joint work with Paul from the University of Wisconsin. And Victoria and David from the Vanderbilt University. David must be here somewhere, I guess. Oh, they're up there. And this is also with Benjamin from the University of Chicago. Now, the aim of this talk or this project is basically constructing large network where every box cells are basically a network node, basically. And then we're going to construct, basically determine the heritability of this network using twin data. Then we actually need to do some p-value computation. So that's taken care of by this what we call the Partial homology. So how do we basically what do we mean by the large scale functional network? So we're going to use a fMRI data set for that. And this is basically a subset of the Tennessee twin study with about 200 200 twins. And the ages are around, I think it's over 20. And I'm basically using the subset of this data set, 11 MG twins and 14 digit twins. And the fMRI experiment is basically the monetary incentive delay task. So you have three kind of the reward, $0, $1, $5 as a queue, and some delay. You are basically shown a target, flashing star. You have to press a button within time to get the money and get a feedback. So it's 3 runs of the 40 trials. And so basically you basically speed up the general linear model. And then you obtain the parameter estimate. Then you also need a contrast, where the contrast is basically the $5 trial. And the baseline is a 0 trial. So then you actually obtain a contrast map. So this is our first level analysis. And using this contrast map, we're going to construct the actual network. Now, this is actually a very challenging problem in statistics, because if you construct the covariance matrix or correlation matrix, it's not something that you can actually construct easily. It's what we call the small and large p problem, where n is the number of the images and p is the number of the boxes or number of nodes. Now, in this case, it's a 3 millimeter fMRI, so there are about 25,000 boxes, which are all node. So that basically gives us about 0.67 billion connections. Now, if you have like a DTI or like a much finer fMRI resolution, obviously you will have a billion connections. And it requires actually about 5.2 gigabytes of memory. It's a lot of memory. And just saving this into hard drive, it takes about 3 minutes. Also, you need to load it. So it's total 6 minutes per connectivity. That's a lot of the time. So if you want to try to do something like a permutation test, it will go forever. You cannot do permutation tests on this kind of large-scale data. So that's the motivation for doing something totally different. And our approach, we can do it in 18 seconds in a laptop, any kind of laptop. We are not using any cluster computing. We are not using any parallel computing. We don't need it. And so because of this very dense connectome, actually, we need some sort of the way to build out the edges. And the most often used methodology is sparse network modeling. It's basically optimization-based methodology where you actually optimize based on the L1 norm penalty to basically build out the edges, actually. Now, here's our technique, actually. First, you need to actually center and scale the data somehow. So, assuming you have a paired images, xk and yk, you basically make a vector out of those and center them, basically, and then also you need to scale them. The reason we do this is that any kind of correlation is a scale invariant and the center invariant. So it will not affect your computation for the correlation, actually. So it's perfectly fine operation. And you will see that if you do this, formulation becomes essentially trivial. So we're going to set up the regression between boxes across the twins. So if you have voxel position Vi and Vj, I'm going to set up the regression model. It's a very simple regression model. So I'm going to correlate the value of the second twin to the value of the first twin, xvi, and the connectivity strength is basically determined by this regression parameter, beta ij. Now, obviously, you can estimate this. We're going to actually need to solve this for every possible pairs, actually. Then the usual estimation technique is a risk-based estimation. And if you do that, nice thing happens, actually. The estimation is basically give you the sample cross correlation is your risk estimation for this problem. And this solution is actually very simple because of the centering and translation, actually. Then what I just shown to you is what we call the least squares estimation. This is okay for the small number of nodes, but if you have a lot of number of nodes, you need to basically construct a sparse network. The way you do is that once you have the L2 norm, you simply add the L1 norm with some sparse parameter lambda. So then how you construct the actual network, binary network? Binary network will be constructed by the adjacent matrix where the beta head is basically estimated sparse edge weights. If those are not zero, you assign value 1, otherwise 0. That's how you construct the binary network out of this kind of the sparse correlation network, actually. And this is an example. I want to remind you that the cross correlation basically gives you the directed graph. So that's why it's not a symmetric graph, just like, so I'm only going to show you the example of the upper triangle, and that can have this kind of direction. Now, in this case, if you perform this sparse cross correlation, you will end up with this kind of the less dense network with in this case, 2 edges are actually deleted. Obviously, estimate the edge weights will become actually different once you solve the optimization problem, but the underlying, so that's how you do it. Now, the problem with this formulation is that it's very time consuming to solve this problem. If the P becomes like 1,000, 10,000, I don't think anybody can solve this problem with a 10,000 node, actually. So we actually developed mathematical solution to this problem. We simply shown that in this paper, actually not this paper actually, a simpler version of this statement is actually shown in this paper. Using what we call the soft thresholding technique, we can show that without any kind of numerical optimization, simply thresholding the cross correlation at the sparse parameter, I can get the exactly identical binary network. So without actually using optimization, obviously computation speed will be 10,000 times faster. That's why I'm able to compute everything in a laptop. It's basically a thresholding technique. So this is example. If you have a sparse parameter 0.3, you will end up with this kind of the sparse network. Identical network can be obtained with this simple thresholding technique. With different parameters, same thing. Now, this is an example of the computation. Now, for this one, I actually didn't use any kind of optimization because I just shown to you that mathematically, you can get the identical network by simply thresholding the cross correlation, and this is what we have actually here. So it's MG twins, digit twins. If you look at it, MG twin has a much higher correlation in the edge weights actually. So this is a different view, and if you enlarge this part, I just want to show you the detail of the network. As you can see, every voxel is a network node actually. Now, if you go really high sparse parameter, you're not going to see much of the edge connection. So I have actual control for the amount of the edges present in the constructed network. Now, I actually did some sanity check. This is the kind of technique I recommend a lot of people for checking the validity of your network modeling framework. So in this case, I basically randomly permitted the pairs so that there's no twin correlation, and you are expect to just get a random connections. And at the sparse parameter 0.7, I'm not getting any connection at all. So it seems like the framework actually works okay for this data. So so far I constructed a sparse network, large scale, and why don't we actually compute what we call the heritability index at the graph level. So for this one, actually, we actually use the ACE model. There are a lot of models out there, but most of those models is likely going to be based on what we call likelihood methodology. That's not going to be scaled very well with a large data set. So I think this is the only model, I think probably not the only model, but the model I found to be scalable with a large P. So using this model, we actually able to identify the amount of the genetic contribution, which is A here, and it's using what we call the Balcones formula. By solving this, it's basically twice the correlation differences between the MG and DG. So this is example, MG twins and DG twins. And for a bunch of twin pairs, we actually compute the twin correlation. And as you can see, MG twins has a much higher correlation compared to DG twins. And if you do the twice correlation difference of this, you get the heritability index at the voxel level. So this is what the voxel heritability index, as you can see, a lot of brain region is heritable actually. Now, I want to extend this to the more like a network level. So now what you're actually seeing here is actually voxel level heritability index of the contrast map actually. Now I want to correlate the contrast map across different voxels and want to compute the heritability index. How you do that? Well, we need to extend the concept of the heritability index to the multivariate fashion. So if you compare the definition of the heritability index, it's twice the twin correlation differences. So instead of using twin correlation, I'm going to use cross correlations. So it's a cross correlation of MG twins and cross correlation of DG twins. And I just extend it to the multivariate fashion. And that's the computation there. Now, what's the diagonal entries of those HGI? The diagonal entries of HGI is then, it's simply the HI. And diagonal entries of the cross correlation is just a correlation. So that's give you the node information. Diagonal entries basically give you the node information. And off diagonal entries give you the edge information. So using that, we just construct the heritability graph index and parameterized by the sparse parameter like this. As you can see, almost most of brain region is kind of heritable, I guess, for this particular experiment. And now, then question is how you actually quantify. I mean, everybody want to know the what p-value. Everybody want to compute p-value rather than the HGI or HI. So here's how you actually approach this problem. We're going to use what we call the graph filtration and, within the framework of the Poisson homology. So you first need to define a collection of networks over some parameter space. And we're going to use basically infinite collection of networks at every possible sparse parameter. You can do it. If you're using the optimization-based technique, you cannot do this because it's so much computation. Each computation of the network will be a couple of hours. So it's going forever. However, because each network is you can compute it in 18 seconds, you can essentially compute as many networks as you can actually. Then, assuming you have this kind of collection of networks, you actually assuming also you have some property where the property has some very specific structure. It's what we call the monotonicity property. So as the parameter increases, you have basically a subset structure. It's a nested network, actually. And this concept, actually, we actually introduced this concept in 2012. It's a paper by Dr. Haekyung Lee. She has the talk on Thursday about the position homology, so you can hear more about the position homology. Now, so what we do is that we use sparse parameters as a parameter to build the collection of nested network. So if you at each sparse parameter, 0, 0, 1, 0, 0, 3, 0.4, 0.5, you have a less dense actual network. Its network becomes more sparse. So each network is, if you look at it carefully, each binary network is actually subset of each network at the higher sparse parameter is a subset of the previous network actually. Then you actually need to define some graph theoretic features. However, you don't want to use any kind of graph theoretic features. You want to use a graph feature that is monotonic. For example, the number of clusters, size of large clusters. For example, another example would be the degree. And then you actually form this monotonic function, and everything will be monotonic function. Now, you may wonder why we want to use a monotonic function, because it gives you a lot of stability to the actual p-value computation. And if you have this monotonicity property, you can actually get a p-value exactly mathematically without any kind of the resampling technique. So the test that we're going to use is that we're going to use the maximum of this monotonic function differences. So in this case, digit twin, mg twin, where it's the number of clusters over the sparse parameter. And when you increase the sparse parameter, obviously you increase the number of clusters. And so those differences, you take a maximum, and the p-value is very small. So that's basically the p-value for the significance of the HGI. Now, you can also do it with the size of the large cluster, and then p-value. And the formula for computing p-value is exactly this here. It's a sum of the exponential functions. And the proof is given in this preprint. So you can take a look at it. And then the discussion is what I actually presented here is more like an infinite scale network model, where because since we are actually using an infinite number scale as a sparse parameter is basically give you the scale on the number of the density of the connection actually. And also I would say that a lot of people here use simply threshold edges, and that's actually not a bad idea. In this particular case, if you're using correlation, thresholding correlation is actually equivalent to the sparse network model. So I recommend you to simply threshold edges whenever necessary, instead of using actually sparse network. You don't need to use a sparse network model. And you can also compute the p-value exactly, analytically, mathematically, without any kind of the resampling technique, if you formulate your problem very carefully. So that's my end of my talk. Yeah.
Thank you very much. And we're doing well on time, but just to make sure we remain on schedule, we'll hold questions to the end. We should still have some time remaining. So thanks, Moo. The last speaker will be Dr. Victor Solo from the University of New South Wales.
Okay, so I'm going to talk about conditional mutual information. That word conditional does not appear in the program, but it's a crucial word. So this is joint work with my collaborators at the Martinos Center, 2 physicists, 2 electrical engineers, and an MD. A lot of the heavy lifting computation was done by Martin Lucy, who, by the way, is Swiss. Okay, so with a bow to Hilaire Belloc and apologies to Rudyard Kipling, let me tell you what I'm going to talk about. So motivate this by personalised medicine, but there are other motivations as well. I'll need to say a few things about networks, and then I'm going to hammer into correlation maps. Then I'll introduce conditional mutual information, raise the issue of constructing individual functional networks from conditional mutual information and show some application to Human Connectome project data, and then a summary. That picture on the right side is a snap of what the results are going to look like. The one in the top left is a correlation circle plot showing connections between different brain regions with the strength of connection, meaning the line is thicker. The next one is a partial correlation plot, which is a plot of direct connections. The one on the left is the conditional mutual information, which obviously I need to discuss. The one on the right bottom is DTI, so that's an anatomical reference. We know DTI is a bit noisy, but it's still a relevant and useful thing to compare to, and we'll be talking about comparison shortly. Okay, so personalised medicine, I don't need, I think, to tell anyone in this room about the emerging idea that brain dysfunction could be partly due to disruption of network structure or function or both. Great interest in pursuing this idea currently, of course. But in order to enable this, you need to be able to construct individual functional networks reliably. So, for example, that you could use biomarkers from an imaging point of view. Of course, biomarkers might well be developed from other angles and perhaps multimodal as well. But the neuroimaging angle is what we're emphasizing here. Well, there's a problem because it's not been possible using correlation maps to develop reliable individual functional networks. So far, that is using only the individual's data. So far, it's been done by averaging over many subjects, and the problem there is you bias towards the group and you may remove your ability to detect anomalies. I've referenced a joint work with my former PhD student, Ben Cassidy, who's now at Columbia doing a postdoc. This is another approach which I'll mention again briefly, related to the one I'm going to talk about now. Okay, so let me point out a few things about networks which I think really we need to bring some clarity. So networks, of course, are nodes connected by links, and networks have two features. They have structure or architecture, and they also have function. That is, the function is how the network is used. So an anatomical network, for example, only has structure, doesn't have function. And by the way, time-varying structure is not dynamics. That dynamics is something else. What is function? Function is found from an analysis of the network traffic, or if you like, the network activity. That is the dynamics. The dynamics is the interaction between the nodes. Currently, the way we're constructing networks is by thresholding noisy link weights. This is done in two ways. A strong threshold gives a binary weight, and a weak threshold removes the noise but leaves an analog, that is a continuous valued weight. Now, here's the crucial thing, which I think is kind of missing from a lot of approaches in this community and elsewhere. Obviously, structure tells you something about function, but it does not tell you everything, because it doesn't take the activity into account. So the graph analysis, it's not graph theory, it's graph analysis that's currently being used, deals only with structure. Small world networks being the best known example of this. There's nothing wrong with that. You certainly need to look at the structure, but you are not going to get everything by just doing that. You need to use something else. Now, there's a set of techniques in the stat community and also later on developed in machine learning, which I call graphical modeling. I'm not going to have any time to talk about these things. This is not the same as what Tom Nichols was talking about with the block models. There are books on this subject, and these use analog conditional weights and are capable of addressing directly the question of function. So I'm going to be using, going the first step along this route. Okay, let's now get stuck into correlation. So it's already been mentioned we've learned quite a bit using correlation maps, either voxel-wise or parcellation-based. I'm going to focus on the parcel-based approach. There are basically four difficulties with correlation. Firstly, the correlation map depicts mostly indirect connections. That is, node A is correlated with node B, not because they're related to each other or interacting, but because they're both driven by node C. And those indirect connections dominate. What is my evidence for that? The picture I showed you at the beginning, that correlation map was a dense map. But when we corrected for the other variables to get the partial correlation map, a lot of that stuff is gone. Now, it turns out the partial correlation map has thrown away a lot of the direct connections as well. But it makes it clear that most of what the correlation's showing you is indirect. And this is a problem because if you're going to try and do some scientific analysis, you're going to be misled. Second thing is autocorrelation. We've understood since the 90s in fMRI that autocorrelation's got a lot of information about network behavior. Somehow we continue to ignore it. The Scott-Me paper I mentioned takes it into account, and in fact, just because of that, is capable of producing reliable individual functional networks. The correlations are incredibly noisy. For a single correlation, the classic formula for the plus or minus 2 standard errors is 2 over root t. T is the number of time points. So with 90 parcels and 180 time points, that's a typical set of parameters for an fMRI experiment, you get plus or minus 0.15. There's something called random matrix theory. It has its origins in physics and statistics and is really the theory that's behind what Mu was alluding to with the big N, small p problem. And there's some result that show you that the maximum correlation has a standard error under a null hypothesis of white noise of plus or minus 2 root log, square root log t over root t. And in this case, it's plus or minus 0.34. So that is when you show, you see a correlation map, the standard error, plus or minus 2 standard error limits are plus or minus 0.34. That's a range of 0.68. That's how noisy those things are. By the way, it seems to me a lot of standard errors being shown at this meeting currently must be wrong. Okay. The fourth problem is there's a huge information loss. So in order to compute the correlation matrix on your, say, 90 parcellated or 167 parcellated brain map, if it's HCP data, you've got to reduce the number of voxels in each parcel down to 1. There's usually 3 ways. One is to do a PCA on each parcel and take the top PCA. Another one is you just average over the parcel. And the third one is you find the voxel in the parcel with the maximum activation and use the time series from that. There's not huge differences between these things, but here's the problem. The top PCA is only going to account for about 10% of the total variation. So if you're just going to only use that, you're throwing 90% of the variation, that is 90% of the information out the window. These are the reasons why it's not been possible to produce reliable individual functional networks using correlation, that is using only individual data. So what are solutions to these issues? Well, the partial correlation addresses the indirect connections by regressing out the effect of all the other variables. And then the Scott-Me method that we developed also deals with the autocorrelation. But the one I'm going to talk about now is a vector approach in which we don't throw away any of the voxel time series. We use all of them. And in order to do that, of course, we can't use correlation. So I need to introduce another association measure, mutual information, and in particular conditional mutual information, or if you like, partial mutual information. Now, mutual information came out of communication theory and electrical engineering. Shannon is the famous name, and this was developed initially in the 50s. Marginal mutual information's been used a lot in image processing, for example, for segmentation and also for image dewarping or alignment, if you like. But what I'm going to use is conditional mutual information, and this is almost had no application at all. So this is something very different. Now, I don't have time to explain the details of mutual information. It's a nonlinear measure of association If you have a look in the corner entry, I've got a formula for the mutual information between two random variables x and y, minus a half the log of 1 minus rho squared, the correlation. So it's a nonlinear mapping, monotonic mapping of the correlation in the scalar case. And in the scalar case, if that's all you're doing, well, really you're not gaining anything. In the vector case is when it starts to get interesting, because the formula is a determinant, or if you like, a sum of logs of 1 minus the square of the canonical correlation. Some of you will know about canonical correlation. So to get the canonical correlation between two parcels, you look for the linear combination of the time series voxels in each parcel, which gives a maximum correlation. That gives you the top canonical correlation. You then go looking for the second best possible correlation, taking linear combinations, but they have to be uncorrelated with the first one that you already took, and you keep going. And if you have two parcels, let's say one with 1,000 voxels and the other one's got 430, you'll end up with 430 canonical correlations, and you use them to compute the vector mutual information. And that's what we're using. In the title there, I got the word decomposable. So, in analysis of variance, you can decompose variation into a sum of contributions from different factors. Maybe many of you are not aware that there's a complete nonlinear extension of that idea, whereby you decompose likelihood ratios in a nested sequence of hypotheses. If you take the expected value of those likelihood ratios, you get mutual information. So you can decompose the mutual information using then something that's called the chain rule into contributions from your sub-hypotheses. So that's a crucial property of this measure. It characterizes independence. So X is perpendicular independent of Y if and only if the mutual information between them vanishes. So you can construct a graph now by just joining only those links that have a non-zero mutual information. If you thresholded a noisy one, then you'll get the same thing you get by thresholding correlations. The strengths will look different. Now, when we move to the conditional case where we regress out the effect of all the other voxels, this is a computational challenging thing to do, which I'll explain in the next slide. But the formula is similar. You're just now using partial correlation or partial covariance matrices, or partial canonical correlations. And there's a beautiful characterization then of conditional independence. The time series at two parcels x and y, conditionally independent given all the other parcels, all the voxels in them, if and only if the conditional mutual information is zero. So you can construct graphs by joining up parcels whose conditional mutual information is non-zero. So that's the basic idea. What about the computation? P parcels, there'll be P into P minus 1 over 2 partial covariance matrices. You would need to do that many linear regressions if you did it directly. And that's very challenging. 167 parcels. You'd need about 14,000 linear regressions. It's not really feasible. Some clever linear algebra reduces it to P multivariate linear regressions, and so you can calculate the conditional mutual information in a matter of maybe minutes or fractions of an hour. But there's another computation that is a big problem, and that is to do the thresholding, you need to have null distributions, and they have to be done currently by massive simulation. And unlike mu, we've had to use every cluster we could lay our hands on at Harvard, and even then it took weeks. So you can draw the pictures in 10 minutes, but you need weeks at the moment to calculate the thresholds that I'll show you. We're working on that. Random matrix theory might come to the rescue there. So HCP data, the 10 unrelated subjects data is what we're using, 4 males, 6 females, standard parcellation, approximately 15-minute scans for each subject, so 1,200 volumes for each run. There's a little bit of additional processing, but it's all fairly standard, and we use something called space to do the partial correlations. So this session was titled Skeptical. And I'm afraid to say that sometimes one of the speakers has to be skeptical about some of the things that the other speaker said. So I disagree with Mu about thresholding correlations. You can't. You actually have to do the regression, but space is very fast, and there are even faster things, in fact. Okay, so here is the overview. We've got brain parcellation. We've got large numbers of time series in each parcel. We keep them all. We calculate these partial covariances. We get the conditional mutual informations, and we threshold, having done the massive simulation. Okay, so here's a blown-up picture of the thing I showed you at the beginning. You can see now some of the brain regions. You can see the connections. Indeed, you can see the correlation map has got a little bit of a similarity to the DTI, but there's a lot of other stuff there as well. You can see that when we've removed the impact of other nodes to be left with the partial correlation map, it's very disappointing. And my suspicion is that although there have been some papers using partial correlation in this community, they've been done on very small networks. And I think probably those of you that tried to use partial correlation so that you wouldn't be misled by indirect connections were extremely disappointed by the kind of result that's shown in panel B. Panel C shows the results of using all the voxels in the parcels and then constructing the picture by thresholding the conditional mutual information. And it looks a lot more like the DTI. If you look carefully, though, in the visual area, you can see some cross-hemispheric connections which don't appear in the anatomy. Actually, other people have noticed these kinds of things using other methods. And there's some interesting questions there, whether there's some functional stuff going on that the noisy DTI is missing, or whether there's still some noise left in the conditional mutual information. These are good questions. We don't have the answers yet. We dug down to look at a particular subsystem, the limbic system. So there is the correlation map in the corner to be compared with the DTI. And again, the correlation map's dominated by these indirect connections. When you've done the partial correlation to display direct connection, well, it's really hugely disappointing. There's nearly nothing there. The CMI, though, is much more interesting. It, again, looks very much like the DTI and is showing a lot of stuff. Steve Stufflebeam, the MD neurologist, ran his eye over this extremely carefully and was pretty happy with that CMI map. It looks, he said, a lot like more detailed anatomical limbic maps that have been created. So this is pretty promising, we think. We've tried to do a little bit more quantitative comparison. I don't like these pictures, but everybody seems to draw them. Correlation between anatomical connectivity and correlation itself, an association of 0.17. Partial correlation bumps up to 0.27. CMI way up to 0.58. This one I think is a bit more interesting. Have a look at the bottom panel. We tried to measure the repeatability. So the bottom panel is the percentage of links that show up in 4 out of 4 sessions on a particular subject. By the way, I should have made clear, I'm not showing you the best possible results. The results I've shown you are just for subject 1 in those 10 subjects. We've done all the other subjects and the results all look pretty similar. And also we've just chosen a 0.05 p-value to do the thresholding. If you vary the thresholding, the pictures look very similar, as long as you don't vary it too hugely, obviously. Well, you can see the CMI has got about a 70% repeatability across all 4 spans, and none of the other methods come anywhere near that. So that, again, we would regard as very encouraging. Okay, so final story. Correlation can't deliver individual functional networks of individual data. Yes, I know Russ Poldrack's group did heroic work scanning, I think himself for 14 hours and managed to do this. But I don't really think that's going to work in general. Our approach can be used on traditional data and appears to be capable of generating reliable individual functional networks. Gives direct connections, it's repeatable, shows a strong relation to anatomy. We think there's a lot of potentials to be pursued here in terms of biomarker development, detecting group differences, precise personalised medicine, and also other things like, for example, focal epilepsy. Okay, so I think I can call it quits at that stage.
Thank you very much, Victor. And we have some time remaining, just about 10 minutes if there are questions. And I'd like to invite the speakers up to answer them. Okay, while you're thinking, I think I'd first like to thank the speakers and congratulate them on 3 excellent talks. I think there were many notable contributions revealed in their talks. One, for Tom Nichols, I think it's great to have a framework for connectivity where we're able to incorporate covariates. Oftentimes we're left with just looking at the structural maps and making comparisons between those, but not necessarily being able to therefore adjust for various covariates. So I think that's something that was a sort of a small point in your talk, but I think a really important one and worth emphasizing. Mu did a tremendous job in adding sparsity to cross-correlation, allowing you to scale the problem. These problems have such high dimensionality, and with billions of things or half billion in your case, the reality is all aren't going to be important, and it's a matter of kind of teasing out the noise and honing in on the more important ones. And so the sparsity and then the numerical optimization obviously was key as well. But then I think the novel aspect of using persistent homology to examine the topological structures of the network property was a great contribution. And then Victor, your talk as well, I thought you did an excellent job of really overcoming some of the pitfalls that were highlighted at the beginning. So retaining a lot of the voxel level information. Again, we understand why we reduce the dimensionality for computational facility, but incorporating that voxel level information is important. And then I think none of us could miss the direct versus indirect message in your talk. You made that point loudly and clearly. And then another subtle point, reducing something down to a Wilks lambda statistic is nice because we have so much theory and statistics about the properties of that distribution. So if you're not in a non-parametric case, it's nice to be able to map on to existing theory. So I just wanted to summarize those. Any questions from the audience? Yes.
Maybe a question for Victor. So very elegant talk, and I like the ideas quite a bit. But I worry a little bit about trying to compare or constrain the functional connectivity with the anatomy, because while you get the monosynaptic, the direct connections, functional connectivity, at least theoretically, shows you polysynaptic or multiple connections. So when you don't have a single neuron or bundle that joins A to B, but in fact A, B, and C are connected, you don't see that with DTI, but you do see that with functional connectivity. So can you talk a little bit about what you lose when you use this approach?
Okay, yeah, well, thank you very much. Agreed, functional and anatomical or structural are not the same thing. And there are well-known difficulties with DTI, which I alluded to. On the other hand, one does expect there's going to be that connection or a relation between the two. So one is kind of looking to that. I don't think the conditional mutual information excludes the possibilities you're alluding to. I think one of the issues here is we haven't really been able to generate these reliable kinds of maps, and now that we can, I think we can start digging in to the kind of stuff that you're raising. We've got a long way to go. We need models, we need theories, we need approaches, we need ad hoc methods, we need model-based methods. So don't have any answers to that question yet, but I think this is one of the techniques that's going to, help sort some of that out.
Thanks.
That's a great question, and I think it comes down to having a basis for comparison, and that's always an issue in experimental studies. I know Tom has been involved with Steve Smith and others on using simulated data, and that's excellent for that particular simulation, and we can learn certain things about our methods, but clearly, that's not a gold standard necessarily as well. So it's always an issue. Question in the back?
Yes, please. As we know that mostly we use the correlation, especially Pearson correlation, to evaluate the connectivity, right? And especially in the resting state fMRI. But maybe it is because most of the medical guys, like me, is not very good at the mathematics. The Pearson correlation is really simple, but there are a lot of disadvantages of using correlation. So does it really make big difference? We use different correlation evaluation, like use partial correlation. Does it? Can we get a different results, or can we deny the some sparkling biofindings when we use different this kind of correlations?
Okay, so I take your point about the math stuff, and I guess it's the job of the methodologists in this community to grind that down so that the neuroscientists can understand it and use it. And it's not so easy to do, but that's part of our job. So we're working on that. And I should say that I've certainly been pummeled rather badly over the last few years while we've been putting this together by my Martinos colleagues, asking just those very kind of questions. To the rest of what you say, well, I think I showed that. I mean, the pictures I showed you are starkly different between correlation, partial correlation, and CMI. And the great hope is that you can start seeing stuff which you expected to be there as a physician, which correlation was simply not showing you. So again, I think this is a beginning, and I think there's enormous potential, to find those things.
Thank you very much.
And conversely, Victor, that you will see things from using Pearson correlations that may be spurious and lead you to false discoveries, if you will.
Can I just add a historical note, since history gets mentioned in this community? It should actually be called Galton-Pearson correlation. Galton, a cousin of Charles Darwin, was the guy who invented correlation in 1868. Pearson was the guy who mathematized it in the 1890s.
Yes.
Yeah. Great set of talks. I had a question for each of the speakers. I was curious if Tom could comment on model order complexity in those block models, and Mu, maybe you could comment on this, the fact that you have infinite scales with this lambda free parameter, and whether the theory sort of generalizes to compute like statistics for across scales. And I guess, Vic, I was going to ask you about potential pitfalls in computing mutual information, say kernel methods. I mean, you pointed out in your thing about Gaussian, which directly is analytic, but if you want to go beyond that, or maybe you could comment on some of the issues of pitfalls of computing mutual information.
And we have about 1.5 minutes, so try to be brief in your answers.
My portion of that very quickly. The model complexity is built into that, so at least the Erdos-Schrödinger mixture model implementation of a stochastic block model has a penalty for the size, and it does. You basically have to try lots of different model orders, but then you compare those with a likelihood-based method to see which one is best. So if you use too many, if it gets too complex, you will not have a good score, and you won't use it. So that's part of the model.
Yeah. The theory I present is very general. However, it has a limitation. It only applied to the up to now correlation and cross correlation. Now it doesn't apply to the partial correlation. It does not apply to the canonical correlation. So Victor is actually right to criticize that you cannot really threshold the partial correlation. However, you can threshold correlation, and cross correlation and get the equivalent sparse network. If I work for 2 years on the partial correlation, I think I may get something similar result on a partial correlation as well, I think.
Okay, so about alternative methods, certainly most of the signal processing application of mutual information are based on these non-parametric approaches. The proof here is in the pudding. We're getting fantastic results using Gaussian, and fMRI is roughly Gaussian. So I think there's a long way to go on that. Doing non-parametric, it's prohibitive, except it may be possible to get some distance using the so-called kernel trick. And we'll have a look at that. But I think the Gaussian story is going to take us a very long way.
All right, terrific. With that, we'll wrap up the session, and please join me again in thanking the speakers.